In this last video, we're going to put together the chain rule that we've been talking about for this whole section, and we're going to look at some examples that combine it with our product rule and our quotient rule, because oftentimes we will be required to use more than one derivative rule. So I want to show plenty of examples that show as many different combinations as we can look at. So first up, I have y equals 2e to the x times x cubed minus 6 raised to the 5th power. And the very first part of these problems is just identifying what derivative rule do I have to use. If I look at this, I see, first of all, I think I see 2e to the x times x cubed minus 6 to the 5th power. I'm multiplying 2e to the x times this other function. Start off, this is a product rule. So this is a product rule. And will I need anything else? So maybe let's look at the derivatives of each one of these separately. Derivative of 2e to the x, well, I know how to deal with that. But the derivative of x cubed minus 6 to the 5th power, when I take the derivative of this part, this is going to be a chain. So this is a product rule and a chain rule. And when we have more than one derivative rule kind of happening at once here, I would strongly encourage you to slow down, take smaller steps, because it's really easy to make a mistake with these. So I'm going to start off, I think, with my product rule, because that's what I identified first here. Remember our product rule, if we go all the way back to when we started to talk about the product rule, we said, okay, how about I call this function f and this function g? And I think that's actually a pretty good place to start right here, just to kind of break it down as much as we can so that we are really taking smaller steps. So if f is 2e to the x, I know that f prime derivative of 2e to the x will simply just be 2e to the x. G is that second function, that's x cubed minus 6 raised to the 5th power. And when I go to find g prime, here's when I need to use the chain rule. It's when I take the derivative of this part of my function, this x cubed minus 6 raised to the 5th power. So using those formulas that we've established earlier in this section, we say, okay, this kind of looks like u raised to the nth power. Okay, so this is a power rule. I multiply by my power. Inside part stays the same, so x cubed minus 6, that part stays exactly the same. Subtract 1 for my power, so I should have to the 4th power, times the derivative of the inside part, times the derivative of u. So multiplying by the derivative of x cubed minus 6, that would be 3x squared. And then if you can simplify this, like I can multiply 5 and 3x squared. Let's go ahead and do that as well. 5, let's see, I should have 15x squared times x cubed minus 6 raised to the 4th power. So I'm kind of setting it up to use my product rule. I haven't really applied it yet, but I've done the necessary setup to say, okay, now my product rule, when I go to apply it, I know it says f prime times g plus f times g prime. And I have f prime, I have g prime. Kind of done all of the heavy lifting in advance, so now I just need to take what I found and plug it into this formula. So let's see, f prime is 2e to the x, so when I find my derivative, y prime, this is f prime 2e to the x, times g, that's going to be x cubed minus 6 raised to the 5th power, plus f, well that's also 2e to the x, times g prime. Here we're going to multiply by our g prime, the simplified version over here. So that is 15x squared times x cubed minus 6 raised to the 4th power. So this is my derivative. Now, I will say these problems, they're difficult. They involve more than one derivative rule. The simplification of them at the end is even more so, I think. It's even a little bit more difficult. So I'm going to show you what simplifying like this would be, but honestly, if you gave this to me as your answer, I think that would be okay. I might just, you know what, I might just say let you multiply 2e to the x and 15x squared to get 30x squared e to the x. But even that I don't think is that big of a deal. If I did want to simplify this, I'm going to factor. So first of all, I'm kind of looking at this as a term and this as a term. Between those two terms, I see, first of all, 2e to the x, we have that in common, so we can factor that out. So we can factor out 2e to the x. Then I've also got these powers of x cubed minus 6 and x cubed minus 6. I can't take away x cubed minus 6 to the 5th because this only has 4 of those powers to take. So I'm going to factor out x cubed minus 6 raised to the 4th power. So what does that leave me with? So I factored out 2e to the x from this term, so this part's gone. X cubed minus 6 to the 5th power, well, I factored out 4 of those, which means I still have x cubed minus 6 to the 1st power for this first term right here. That's this guy. Plus, over here, this, I factored out 2e to the x, that part's gone. X cubed minus 6 to the 4th, well, I factored out all 4 powers of those, so the only thing I'm left with then is this 15x squared. So plus 15x squared. That's all that's left from this term right here. And again, you could probably leave it here at this point. Honestly, I think the only thing I would do, x cubed minus 6 to the 1st power, we don't really need that here, since anything to the 1st power is itself. So I would drop that. I would drop the parentheses. Combine any like terms, but in this case I can't. So you know what? I would just say, you know what? This looks like our derivative. So simplifying these at the end can be really tricky, and that's something that I'm less concerned with doing now. We may look at a problem or two in the future where we have to simplify something that involves more than one derivative rule. But for right now, I'm really focused on, can we apply both derivative rules to kind of get this raw version of the derivative, this unsimplified version, that really shows me that you can use both the product rule and the chain rule. That's mostly what I'm concerned with right now. So let's look at the next example. Next up, I've got f of x equals natural log of 1 plus 3x divided by x to the 5th. Hopefully we look at this, we say, boy, that looks like a quotient rule, because that looks like a fraction. I think the quotient rule is the easiest of the bunch to pick out. So this is definitely going to be a quotient rule. So this is a quotient rule. And then what else? Well, x to the 5th I know how to take the derivative of, but natural log of 1 plus 3x, that's going to be a chain rule. So this is a quotient rule, and it's a chain rule. So again, just like I did last time, I think I'm going to take these functions off to the side. And we used what? Low and high, low D high, and all that jazz for quotient rule. I'm just going to use y, just because I don't want to worry too much about it. Y, or my high right here, would be natural log of 1 plus 3x. So when I take the derivative of this part, y prime, so let's see, natural log of 1 plus 3x, we said that was u prime over u. So the derivative of this inside part, derivative of 1 plus 3x, would just be 3 divided by u, which is just this inside part. That part stays exactly the same. So 1 plus 3x. There's my derivative of just my numerator, just the numerator. For the denominator, y equals x to the 5th power. If I take the derivative of that, that one's not so bad. That's 5x to the 4th power. So at this point, the chain rule, I did all of that chain rule work right here. I'm done with the chain rule for all intents and purposes. Now it's just applying that quotient rule. Which isn't to say it's easy. It's going to be very messy here. Because when I go to apply this quotient rule, let's see. f prime of x. Quotient rule says low, that's x to the fifth, so x to the fifth, d high, derivative of my numerator. Well, I already found that. That's right here. That's 3 divided by 1 plus 3x. So let's see, 3 divided by 1 plus 3x minus high, so that's going to be natural log of 1 plus 3x. So natural log of 1 plus 3x. D low, derivative of my denominator, we said that was 5x to the fourth over here. So times 5x to the fourth, square the bottom, and away we go. This one really doesn't simplify all that nicely. If it's me simplifying it, really the only thing I think that I would do is I would take this x to the fifth squared, I would rewrite that denominator as x to the 10th. Everything else, I'd really have to get a common denominator right here. Or excuse me, no, I wouldn't. I would have to, that would just be 3x to the fifth over 1 plus 3x. But if I wanted to subtract these two terms in my numerator, then I would have to find a common denominator. So I'd have to get a common denominator, and then I'm dealing with fractions inside of fractions. I don't want to get lost in the algebra here. If you can make it to this point right here, that's what I'm checking for, because that shows me that you know how to use the quotient rule and the chain rule together. So don't worry about simplifying these too much in the end. Part D, f of x equals natural log of x cubed minus 2 squared. This one's going to be a little bit tricky, but it's a really good example, I think. So I look at this, boy, where to start here? I would probably start with this inside part. I see natural log of x cubed minus 2, just like we did earlier. I see that's a chain rule. When I want to take the derivative of that inside part, derivative of natural log of x cubed minus 2, that has to be a chain rule. So it's definitely a chain rule happening here. But then if I look at this as a whole, I have natural log of x cubed minus 2 quantity squared, and mostly I'm kind of interested in the squaring function. Squaring function, look at that inside part. I have natural log of x cubed minus 2. We said if that inside part is anything more complicated than just x, it's a chain rule. So what I have here, ladies and gentlemen, I have a chain rule and a chain rule. So the chain rule is kind of an interesting one in that you can apply the chain rule more than one time. You could have a chain rule inside of a chain rule, or you could have a chain rule inside of a chain rule inside of a chain rule, and that, you know, you could just continue doing that. You could probably break down the product rule that way. You can say there's a product rule inside of a product rule as well, but I think that this is by far more common to see a chain rule inside of a chain rule. So I'm going to slow this chain rule down here. I'm going to look at just this inside part for right now. And just like we did earlier, I'm going to call that inside part u. U is equal to natural log of x cubed minus 2. So I'm going to fall back on that kind of general chain rule that we practiced so much at the very beginning of this section. And then we'll use our formulas coming up here. So u is natural log of x cubed minus 2. U prime, actually, here's where we'll use one of our formulas. We said the derivative, if we're working with natural log of u, it's be u prime over u. So the derivative of this inside part right here, derivative of x cubed minus 2, that would be 3x squared, divided by u, which is just this inside part right here, that's going to be x cubed minus 2. So here is my inside part and the derivative of that inside part using the chain rule. So I've done one of my chain rules. That part's done. I just have to look at the other chain rule. So let's actually make our substitution here. Let's say f of x. I'm going to take this piece out and replace it with u. This is really u squared. And right now, I'll just address this. This is kind of bad notation because I have x and u, and I'm just sort of going to wave my hands and pretend not to notice it, because I don't want to worry about that. So when I go to take the derivative, f prime, we said, okay, you do the power rule right here. So 2u to the first power times u prime. Right, so here I've got, just to differentiate between these two, here I've got u to the first power. Over here I've got u prime. So all right, f prime of x is equal to 2 times u to the first. We have u to the first over here. That's natural log of x cubed minus 2 to the first power, which, to be fair, we don't have to write that to the first power. If you just wanted to write that as 2 times natural log of x cubed minus 2, that's perfectly fine as well. Times u prime. What is u prime? That is 3x squared divided by x cubed minus 2. And there's my derivative. If you really wanted to simplify it, we could say, okay, 2 times 3x squared, that's going to be 6x squared natural log of x cubed minus 2 divided by x cubed minus 2. If you really, really, really wanted to simplify it, you could say that. But again, I think if you can make it to this point right here, that's what I'm going to be looking for, because you've shown me now that you can apply the chain rule and a chain rule. All right, I think we got a couple more here. We just got these two left. Next up, I have y equals x natural log of x divided by e to the x. Again, I see this fraction. That sticks out like a sore thumb to me. This is definitely going to be a quotient rule. This is a quotient rule. And then look at your numerator and your denominator. When I take the derivative of x natural log of x, what I'm really saying is x times the natural log of x. I'm multiplying those two. So this is actually a quotient rule and a product rule. And let's just make sure. Let's see, natural log of x, I know how to take the derivative of that. E to the x, I know how to take the derivative of that. There's no chain rule here. Because we could have, if I was feeling, if I was in a grumpy mood, I could say let's do a quotient rule, a product rule, and a chain rule, all at the same time. But let's start with our quotient rule here. Let's look at the numerator. Let's say y equals x natural log of x. When I take the derivative of that part, x natural log of x, so the derivative of x is just 1, so 1 times natural log x. Plus this time I'll leave x alone, so x, derivative of natural log of x, however, be 1 over x. And I would simplify this. I would say what? Natural log of x plus these are going to cancel, so I'll just be left with plus 1 there. So there's my numerator, derivative of my numerator. Denominator, y equals e to the x. Derivative of e to the x, just e to the x. So I've kind of got this already. At this point, again, I've done my product rule. I did it right here. Now it's all quotient rule from here on out. So the derivative, y prime, says low. That's going to be e to the x. D high, that was this guy right here. So d high, that's going to be natural log x plus 1. Minus high, so that is x natural log of x. X natural log of x. D low, derivative of my denominator, we did that over here, that is e to the x. Square the bottom, e to the x squared, and away we go. So let's see. Again, if you wanted to stop right here, I think that's perfectly fine. If you really want to simplify it, a couple things I think we can do here. We can factor out e to the x. So that would leave me with e to the x. My numerator, I'm left with natural log of x plus 1 minus x natural log of x. None of those are like terms, so I can't combine anything. My denominator, when I have a power raised to a power, we just multiply those two, so e to the 2x. And oh my goodness, we can cancel this even more. This is so exciting. We can cancel out an e to the x, and then in my denominator, that would just leave me with e to the x. So if you really, really wanted to simplify it, this is what your derivative would look like. If you're just looking to get the derivative, though, that's what I would be looking for. Last example for this section, I have e to the 7x, and let's say y. Let's say y equals e to the 7x times the cubed root of x squared. I look at that, and I see, let's maybe rewrite this guy. Let's rewrite that radical. E to the 7x times x to the 2/3 power. So I look at this, I see, all right, e to the 7x times x to the 2/3. That is definitely going to be a product rule. We've got a product rule happening here. And then e to the 7x, when I look at this guy, I look at that power. I notice it's a 7x. That's going to require the chain rule here. So how about I call this guy f? I'll call this guy g. F is equal to e to the 7x power. So f prime, derivative of e to the u. We said u prime, so we're going to multiply by the derivative of our power, which is 7, times e to the u. This part stays exactly the same, e to the 7x. G is x to the 2/3 power. G prime, I just need to use my power rule, so let's see. 2/3 x, I'll subtract 1 for my power, negative 1/3. We could leave our answer with a negative exponent, or if we really wanted a positive exponent, like I prefer, 2/3x to the positive 1/3 power. So at this point, again, I've done my chain rule. I did all of my chain rule in this step over here. It's just product rule from here on out. So I'm applying my product rule. Remember, that says f prime times g plus f times g prime. Let's go and find our derivative. Y prime is f prime, that's 7e to the 7x, times g, let's see, times x to the 2/3 power, plus f, that is e to the 7x, times g prime, we said that was times 2/3x to the 1/3 power. Again, if you wanted to leave your answer like this, I think that's perfectly fine. If you did want to simplify a little bit, all I would recommend doing is factoring out this e to the 7x from both of these two terms. That would give me e to the 7x times 7x to the 2/3 plus 2/3x to the 1/3. You may see, especially if you're following along with examples in my math lab, or if you're looking at solutions in the back of the textbook, if you have the textbook, you may see some answers get a common denominator. That's not something I'm worried about. So if you see a common denominator, that's above and beyond where I want us to go. Again, I want you to be able to show me that you can apply both the product rule and the chain rule together. Usually on exams, I really only throw about 1 or 2 of these on here, so don't get too stressed about seeing them, but I think these are really, really good practice problems. I think that the best way to kind of learn how to identify what derivative rule you're using, whether you're doing a product in a chain, or a quotient in a chain, or a chain in a chain, or whatever the combination is. I think that the best way to learn how to do that is just by practicing. Just practice as many of these problems as you can. If at the end of the homework exercises you're still maybe feeling a little bit unsure, that may just mean, hey, you need to go and find more practice problems on your own. And there's plenty of websites out there that'll have those, but this is going to be really important because in the next section, again, we're still going to be working with derivatives, but we're going to have to know how to take a derivative using a product rule or a chain rule, or even both, kind of on the fly. So I would get as much practice with these as you can. I do think that is going to help you out in the sections to come.